Hey guys, what's up? I am Vaibhav Suryavanshi, educator, academician. Tell you how exactly the PID controller can be worked. In last few lectures, we have discussed what is meant by proportional, integral, derivative, controller, single, alone. What are their advantages? What are their disadvantages? Why we cannot use the derivative controller single alone? Why cannot we cannot use the integral controller single alone? All answers we have discussed in the last few lectures. If you're not seen, you can see on my VJS technical channel. This is available online, so you can just subscribe for the VJS technical channel so that you will get the new interesting video for you people. Let us start with the PID controller discussion. So what is the PID controller? Yes, we already discussed the PID controller is the proportional, integral and the derivative controller. So we have discussed why we cannot use the integral controller single alone. We have discussed why the derivative controller single cannot use the single alone. But yes, we can say that we can use the integral controller along with the proportional controller. Then derivative controller also we can use along with the proportional controller, because the unique characteristics of the proportional controller, unique characteristics of the integral controller and the derivative controller. In this lecture, we have to deal with the how or why we can use the PID control combinedly, or we can say that the proportional, integral and the derivative controller. Before I proceed for the discussion of the PID controller, I'll tell you some of the very interesting questions asked into the mini university exams about the PID controller, that is the proportional integral derivative controller. So what the question asks in one of the exam, that draw the suitable block diagram and derive the transfer function of the proportional integral derivative controller in the series form. Also discuss the significance of the integral derivative terms in the PID controller, that we have to see from here. Before I proceed, I'll tell you why. Because the PID controller can be used in combinedly. What are the exact characteristics of the PID controller? Yes, there are the few characteristics, few advantages of the PID controller. So we can use the PID controller as the question asks. This is into the, we have used into the series form with this comparator, so that we can get the PID controller. This derivates the action interacts with the integral action. Modification of the derivative time constant affects the integral action and commonly used as a controller, which having their own advantages. If I consider the transfer function of the PID in series, we can say P plus PD into bracket 1 plus I, where what? P is the proportional at the controller, I is the integral controller and the T is the derivative controller. So we can define the transfer function as the P, PD, PI and the PID controller, because we have to use into the series. If we are consider the PID is equal to 0 and Ti is greater than the 4 TD. What is the Ti? Ti is the integral time constant. What is the TD? It's a derivative time constant. Then transfer function can be formed as a P, Pi and the PD, because we have considered the PID controller as the 0. We have considered it is having this value. So if we consider the transfer function in the series form, then the control signal for the PID series, yes my friends, PID series is a combination of the proportional, integral and the derivative controller. So ultimately you get the equation for the PID controller as a KPE plus KPKI integral of E dt plus KPKD dE by dt, where E is the error, difference between the reference measured signal. This is the equation of the transfer function for the PID control. If I define into the block reduction diagram, if you see here, this KDS, KIS and the KP we can get from the applying the Laplace transform, as we have discussed previously for the PID control. So you'll get the immensely here by the addition of this with the comparator, you get the plant, and you can actually actuating in the series this the PID controller into that. Because of that you will interact with the system and you will get the very interesting results. Then ideal form, derivative action does not interact with the integral action, because we already see derivative controller is the fractional change with respect to the error, and integral controller also having after a few seconds fractional change. If two fractional changes combine with respect to each other, the combined effect is the too high amplitude, is of the very uh, high amplitude, and because of that derivative and the integral controller cannot be used the single alone. Transfer function for the parallel form, if we have to define, then how we can define? See here, we can add kp ki upon s kd upon kd into the s, that is applying the transfer for our Laplace transfer for the transfer function, where the kp is a proportional gain, ki is the integral gain, then kd is the derivative gain. Then control signal we can get from here, that is u of t is equal to up of t, that is a proportional constant, integral constant, and the derivative constant. If we make the substitution of the integral formula for the proportional, integral, and the derivative controller, we can get it's a kpe plus ki integral of e dt plus kd into bracket t by dt, where e is the error, which is the difference between the reference and the measure signal, that we also call as a feedback control system. See, from the make the system for the PI controller also we can define by just adding the KPI and the integral control, that is a proportional controller and this is integral controller, and we can make the formalization for that is the Kp into E plus Ki integral of E dt. Similar the way we can make for the Kd also. Here proportional integral PI controller helps to minimize the rise time, settling time, as well as the eliminate the steady state error. That's why depending upon the situation, your system is how much complex, your system is how much simple, on that basis we can decide whether we have to use PI controller or PD controller or the PID controller. If your system is simple, you can go for the PI controller also. If your system is require a fast response and it's simple, then you can go for the PD controller. If your system required all these characteristics in a single platform, that time you have to be enter with the PID controller. Okay, on this basis we can define the PID controller, PD controller, and PI controller. So combinedly, if we see what is the transient specification for that, so come to know from that, this for the proportional constant if I use, then the rise time gets decreases, overshoot increases, settling time having a small change, and steady state error also decreases. Integral controller, then your rise time decreases, overshoot gets increases, your settling time initially decreases and then increases, and steady state error gets eliminated. Then into the by using the derivative controller, there is a small change in the rise time, overshoot decreases, settling time also decreases, and the small change into a steady state error. This chart is very important for you people for the competitive exams, because in a Indian engineering services many times these kind of the questions can be asked, that what is the impact of the proportional, integral, and the derivative control, because ultimately this is the chapter included in your syllabus. So if we consider the PID stepwise procedure for the manual tuning, you can come to know with these 6 steps, that is a open and open loop response, and determine what needs to be improved. Then add the proportional controller for the increasing the rise time, add the derivative controller to improve the overshoot, then integral controller eliminate the steady state error, adjust the PID unit until you obtain a desired overall response, referring to the table shown previously, that what we have discussed to find out which controller controls that the what characteristics. It is not necessary to implement the all 3 controllers. into the single system. For the example, if the PI controller is the good enough for the responses that I have discussed a minute before, how much your system is simple, how much system is you require, what characteristic, on that basis you can make your system that is PI, PD or PID controls. Then don't need to add that time T controller to the system. So simple, we can say that simple is always better. So PID stepwise procedure for the manual tuning that we have seen, and from that you can note that it is not necessary to implement all three controllers PID into the single system every time. For example, PI controller, if it is good enough for the response, then don't go for the D controller, that is derivative controller, to the system. And again I said simple is always better. What are the application of the PID controller? There are the 90% processes are controlled using the PID. Regulation of the processes in the industry, for example, flow control, temperature control, pressure control. In the electric field, there is a servo or the DC motor control, linear position control. All these applications governed by the PID controller. These are governed by the PID controller. That's why PID controller can be used. There is one numerical asked, but I think we can discuss this numerical into the next lecture so that you can understand it with the better understanding. Still, till that, stay at home, don't go here and there, be happy and away from the corona. Thank you very much. Goodbye.